that. This course ultimately just talks about vectors in two dimensions. You can carry over everything we talked about here in two dimensions into three dimensions, and pretty much everything we do throughout the entire section or entire chapter so far, we'll be able to carry over into three dimensions as well. It's a very easy transition. There are a few things that you mess around with in different aspect in 3D, but we are going to, like I said, mostly spend our time in two dimensions. Those of you that have taken physics, who's in physics? Just show of hands. Fantastic. So I'm going to be telling you probably a lot of stuff you already know, which is good. Okay. Or hopefully maybe explaining something that you've been taught in a different way so that you can learn it. Okay. Vectors are ultimately not something that should present us great difficulties. Okay. In physics, you probably dealt with vectors in regards to like simple machines, like inclined planes, pulleys, and that kind of stuff, right? Okay. Maybe you dealt with forces, normal forces, forces of gravity, that kind of stuff, right? Maybe in physics you either dealt with or neglected friction as a force. Okay, and if we neglect it, it makes things a little bit easier. But you've dealt with some of that stuff. Okay, vectors are a huge component to kind of understanding, real world kind of phenomenons. Okay, and a lot of times trying to explain movement. Okay, so a lot of our applications for vectors come and that we're going to see and deal with come in like navigation. I already talked about like inclined planes and forces and stuff like that. But vectors, they're all around the place, okay, and they're used a lot. Try to give you as many examples as we move through this chapter where vectors kind of present themselves to you. Okay, used a lot in technology. Okay, so when we deal inside mathematics, we talk about things like, in science as well, things like temperature, weight, or mass, area, energy, age, okay? And those things can all be explained with one value, right? Okay? A temperature, if I give you a value of temperature, how, everything I need to give you is explained with that one number. If I tell you it's 67 degrees outside, then you don't need anything else. I've given you all the information. That's what we refer to as a scalar. Okay, something that can be expressed or explained with a singular value, and that singular value is equal to a magnitude. How large it is. Does that make sense? Okay. When we talk about something that needs some other added requirement to kind of understand it, and that added requirement is what we refer to as a displacement, okay? Then we have an object or an idea or a concept that can be explained with a magnitude or a size and a displacement, or usually what we call a direction, okay? That then is where we use vectors. Vectors are essentially a magnitude with a direction. Okay, so for instance, when I see and talk about, maybe you talk about this in a physics class, when we say speed, if I say 20 miles an hour, 30 miles an hour, 40 miles an hour, that kind of thing, that's a scale. Okay, it's on a scale from 0 miles per hour to whatever, correct? But if I talk about a velocity is now a speed with a particular direction. Okay? So if I say 20 miles per hour northeast, now that is a velocity. Does that kind of make sense? Okay? Accelerations can be represented or are represented with vectors. Okay? An acceleration is the change in velocity. Okay? So those are some things that maybe in a physics class you guys have talked about a little bit. In everyday kind of communication language, you see it on TV a lot of times. the word speed and velocity get interchanged and misused a lot, but mathematically speaking, speed is a scalar, velocity is speed with a direction. Okay. So it says describe the velocity of a moving object. We must specify both the speed and the direction of that moving object. Okay. Quantities such as displacement, velocity, acceleration, and force that involve magnitude as well as direction are called directed quantities. Okay. So a directed quantity, another word for a vector. Okay. Sometimes they call them directed line segments when you see them in some textbooks, but ultimately we start talking about them calling them vectors. Okay. Vectors are used a lot if if I'm flying in an airplane. Let's think about this. Let's fly in an airplane, and let's say we just put the XY axes in here, and we're looking straight down from like a bird's eye view. So maybe there's our airplane. Okay. Let's say that I am traveling that direction. Okay. North, what would that be? Northeast. Okay. But there is a wind that is flying, or that is directed in a northwest fashion. Okay. If my pilot says, "Hey, we're going autopilot. I'm going to take a nap." Okay. And there are no instruments on board that are going to kind of interpret these crosswinds. Do you see that my airplane is not going to stay on a northeasterly kind of path? Okay, that crosswind is going to push it to actually take a course that would be kind of like that, right? Does that make sense? Okay. So we need to be able to kind of interpret what that crosswind is so that we can kind of fly into it, okay? Fly into that crosswind a little bit. So say my airport that I want to get to is right there. If I go autopilot and there's no instruments to adjust, my airplane is going to miss the airport, right? Okay? But if my autopilot has, and even my human pilot has to know this information, if that crosswind is coming, then I need to know, I need to fly, maybe not so much that way, but I need to fly into it so that crosswind will push me towards my airport. Does that kind of make sense? So we need to be able to compensate for those things. If we don't, we're kind of in trouble. Okay. Now I don't know anything about aeronautics in regards to like the instruments that are on board and that kind of stuff. I would venture to say though that they have instruments on board that are going to interpret what those crosswinds are, determine what they are, and then be able to do the math to compensate for them. Okay, that's a common question that we're going to deal with. Same thing, and it doesn't have to be an airplane; it could be like a boat in the ocean or in a current. Okay, same thing happens. Okay, so we need to be able to compensate. Anybody ever swim across a river? Anybody ever swam, whatever the word is, across the river? Nobody's done that? Okay, if I'm right here, and we've got this river here, right? Rivers have currents, right? Okay, let's say that river is traveling at 6 miles per hour. Okay? If I swim, I want to get right there. If I swim straight across, if I head straight across to that, where am I going to end up? I'm going to end up over here, ain't I? Okay? So what do I need to do? This current is going to be able to be represented with a vector. What we would do is we would compensate for that 6 miles per hour, and we would maybe swim over there or in that direction, because now if I'm swimming directly in that direction, the current is going to push me, and eventually I will end up where I want to get to. Does that make sense? Okay? That's something to think about if you're ever in a situation where that's a waterfall, okay, would I want to swim straight across? If you want to go for a ride, YOLO. Yes, exactly. So those are maybe situations in the real world where vectors are right, and there's thousands of others. Okay, you know, how do when I touch my touch key or my touchpad on my computer, and the cursor knows how far to move based off how far I move my finger, right, and in what direction I move my finger. That's vector stuff. Okay. You know, a lot of computer programming can be done and is done with the use of vectors. To be honest with you, there's an entire branch of mathematics that is dedicated to dealing with vectors and understanding vectors, and it's called linear algebra. And you start to investigate the different places and aspects that you can use this stuff and the different, obviously, algebra that you do with vectors. All right, so we'll talk about the geometric description of vectors. The geometric description of vectors is really nice. It's easy to kind of to get a grasp on what we're really doing here. But then the geometric aspect of things becomes kind of cumbersome in regards to answering a lot of questions. So what we develop and understand or realize is that, yes, we have this geometric description, but we can convert that into a more kind of cryptic algebraic description, and then a lot of our algebra that we currently have will work with vectors. Okay, so for instance, we have the commutative property in algebra, right? You can move things around. 3 plus 5 is the same as 5 plus 3. But when we get to adding vectors together, the commutative property exists for vectors. Okay, so a lot of our algebra that we're familiar with will exist within vectors. All right, so a vector in the plane is a line segment with an assigned direction. Okay, so that vector down there, that red vector, has a direction. Okay, it also has a length. Okay, so the length we refer to as magnitude, and obviously the direction we call it direction. Okay, the direction, and we're not going to get to this today. The direction is defined off of SOHCAHTOA. Okay, we'll be able to determine those things here in a little bit, probably on Monday. Every vector, we can view it as a ray. It's going to have a initial point. That's where it kind of originates or starts, and then has a terminal point, and that's where it stops. Okay. The length or magnitude of the vector is denoted using this notation here with the absolute value bars. Okay. We read that magnitude or length of vector AB. However, we've seen this before, haven't we? Didn't we see something just recently like that? Okay. That is because when we graph those complex numbers in an Argand diagram, we add that little directed line segment to the point, right? That little directed line segment is a vector. This was found by taking a squared plus b squared and then square rooting that, right? It's the Pythagorean theorem. If I want to find the magnitude of AB, it is the exact same thing, okay? Because every single vector that we ever come across, unless it's horizontal or vertical, and then it's really easy. Let's say I take that vector there, okay? Does that vector have some horizontal? Oh, I don't want that one to do that. Does that blue vector, the top one, have some horizontal component? And does it also then have some vertical component? Does that make sense? So every vector that you ever come across, okay, will have those two red vectors, okay? No matter how I want to draw that blue one, those red vectors should exist for that blue one. Meaning then that every vector is the hypotenuse of a right triangle, correct? So if I want to find the length of that blue one, I find this red one, which I'm going to call A, and I find this blue one, or sorry, this red one, sorry, this vertical one, I call that B. Then the blue one is going to be found by taking A squared plus B squared under that root. Okay. Is that doable? Okay. Did you guys talk about this in physics, these red ones? Okay, these are referred to as the A vector here. We call that our horizontal component. And this is our vertical component. Did you guys ever hear those words in physics? Okay, so probably when you talk about inclined planes, right? Okay. Every single vector that we ever come across is going to be able to be broken down to a horizontal component and a vertical component. And if you look at this over here on the left-hand side of the geometry, it's showing us the algebraic notation, or one of the many algebraic notations for vectors. Okay. It's calling this one 6,4. Okay. And that's because the horizontal component is 6. That line right there is 6. Going by 2's here and all these blocks. And the vertical component is 4. Make sense? Okay. And that's why you're seeing these red vectors, V and W. Okay. One of them says it's 6 in the horizontal and 0 in the vertical. The other one says it's 0 in the vertical, 0 in the horizontal, and 4 in the vertical. So every vector can be broken down that way. And if it's just a horizontal or a vertical vector, then it's just itself. Does that make sense? We don't have to do the right triangle thing. Okay. But magnitude, length of every vector can be found that way. Now some notation. And I'll try to bounce back and forth between notations because I think that's beneficial for you to experience and see. We can call, a lot of times in like typeset, that we use like a bold U for our vector. V gets used a lot, and W gets used a lot. Okay, those are usually the three letters you start off with, but you can use any letter you want to. But U, V, and W get used the most. Okay. If you are writing by hand, obviously you probably don't want to sit there, write by hand, and try to provide bold letters, right? So U, vector U, can also be written that way. Okay, maybe something you get. Have you seen that in physics? No. All of these things equate to one another. Vector U. Still read this as vector U. This obviously is vector AB, but still U. Okay, we define AB as U. So you can talk about a vector based off of its initial and terminal points, or just call it some lowercase vector. Is that all right? So if I want to talk, magnitude of AB, I could have also said this or that. Okay, they all mean the same thing. Okay, I like this notation. It's the notation you probably see the most in higher level courses. That's the one I use the most often. All right. So if I've got vector U, so let's say we look at this this red vector down there in this whole picture. That red vector, let's call it U. Okay. Would you guys agree that you can take that red vector, slide it around using translations? You slide it around, and it will lay on top of any one of those blue vectors. And then any one of those, if that's the case, then any one of those blue, because of transit property, any one of those blue vectors will lay on top of another blue vector, right? What that means to you is that those vectors are all the same vector. They're all equal. It does not matter where your vector is in the coordinate plane. It doesn't matter where it starts or where it ends. If its length and direction are the same as some other vector, then we say the two vectors are the same thing. Okay? So to determine two vectors to be equal, you need the same length and you need the same quantity or same magnitude. Does that make sense? All right. And hopefully that makes sense. If I want to say two scalars are the same, if I want to say two temperatures are the same, they got to have the same magnitude, right? Okay? If I want to say two vectors are the same, then they have the same magnitude, also the same direction, because that's how we define a vector. So, let's give you some pictures here. If I take, let's say, that vector there, so we're calling that vector u. Okay? And let's say I've got the axes here. And actually, I want to put that away from 0, 0. So let's get it. There we go. So that's vector u. Okay? That vector, is it the same vector? Are these numbers ever changing based on where I put this vector? No. Okay? Now, that being said, then, so that vector is the same as that vector. Same as that vector. All of these are the same, right? Because I can put them on top of one another, and they match up exactly. Okay? Their directions are the same, and their size or their magnitude is the same. Their direction is based off of, let's see here. Their direction would be based off of some horizontal line that goes through the, what we call the tail of the vector, and the vector. So that angle right there would be the direction. Does that make sense? Okay. Well, that direction would be the same for that vector up there, wouldn't it? Okay. Which would be the same then for maybe this vector down here. And that's kind of getting messy now. But the directions are all the same. If that's the case, if these two vector or three vectors are always the same no matter where they're at, algebraically speaking, it would be best for us to reposition these vectors so that they start at 0, 0, wouldn't it? Okay. So that is a tool, a concept that you might want to kind of think about as we're starting to eventually do some problems that involve vectors, trying to move them so they're at 0, 0. Now, if I do this, let's see here. All right, looking at those two vectors, are they the same length? Yeah, they overlap each other, right? But is the blue vector and the red vector, are they the same vector? No, if we just look at this information here, okay, you see over here that they're identified differently, right? Okay. So these are not the same vector. These are actually opposites of one another, okay? If this is u, this blue one, we refer to as negative u, okay? And that's just because the lengths are the same, but the directions are opposite, okay? If we were to put them tip to tail, okay, which is actually going to be that right there, that would be tip to tail, so they overlap each other. Their sum would be 0. They negate each other. Does that make sense? Okay, cancel each other out. The reason they're obviously then different, their lengths would be the same, right? So what would be different about them if their lengths are the same? What would be different about them that makes them unequal vectors? Their direction. If I look at this one's direction, okay, this one's direction would be that right there, correct? This one's direction would be that. Those angles are different, are they not? Okay, so something to think about as we move through and deal with vectors. If I want to have two vectors that are equal, they have to have the same size in the same direction. All right, so this definition of equality makes sense if we think of vectors as representing a displacement. Two such displacements are the same if they have equal magnitudes in the same direction. Basically meaning that if the way I like to think about vectors, guys, and dealing with displacement is to take and say that we're going to put somebody, let's say that the grid here is an empty room, okay? So we take all the desks out of this room, and we put somebody right there at that point. We put them in a rolly chair, okay? And I apply our vector's magnitude is going to represent a force, okay? Maybe I apply 10 newtons in what would look like maybe a north-easterly direction, okay, or a 45-degree direction, okay, or close to that. Put somebody in that wheelie chair, the rolly chair, and I push them, okay, they're going to eventually, once that force is applied, they will eventually come to rest right here, correct? Okay. Well, is that displacement exactly the same if the person were to start right there? Do they get moved away from their starting position in the exact same manner? Yeah. Okay. Now, they don't end up in the same spot, right? But they move away from their initial position in the exact same direction and at the exact same length or distance. So those displacements are the same. All right. Let's get into dealing with what you guys in physics have probably referred to as, or what do you call it when you add two vectors together? Vector addition. What was it? Did they use a tag phrase? Or say tip to tail? Okay, so we're talking about tip to tail here. Okay, we've got these two vectors. Okay, the black vector AB and the black vector BC. And let's assume that those are forces. So again, what I want to do is I want to envision that we've got a blank room here. Okay, and looking from kind of bird's eye view, we've put somebody in a rolly chair at A. Okay, and we applied a force of some newtons in some direction that is going to take that person from here to there. Does that make sense? Okay, so that was the first displacement that we created. Okay, so that we applied our first vector. That person comes to a rest at B, and then say, okay, now I'm going to push them from over here. I'm going to be on this side of them, and I'm going to push them along this vector BC. So I'm going to apply, so that direction, I apply another force of some newtons, and they come to a final rest there at C. Okay? Does that make sense? If we do that, we have maybe, let's say this was 10 newtons, and let's say this was 8 newtons. Okay? From what we have talked about, in our geometry classes a couple years ago, regardless of the type of triangle, okay, that number plus that number have to add up to something bigger than the third side, don't they? That's a triangle inequality theorem, or a component of it that says that the third side of your triangle has to be less than the sum of the other two sides. Okay? Meaning that distance, that red distance, which we refer to as our, we know what we call that? Say again? That's the resultant. Okay? Your resultant vector would be a vector that we could apply to the person sitting in the roll chair at A and get them to C, okay, in the same exact manner that the black vector's got in there. Does that make sense? However, because of this triangle relationship, doesn't the distance from A to C on that red vector have to be shorter than the black vectors have together? Does that make sense? So if I'm in the business of wanting to efficiently move somebody, okay? So we're talking about forces and energy and that kind of stuff. We want to be as efficient as possible, right? So if my only goal is to get somebody from A to C and there's no obstacles in the way, I'm not going to use the black vectors. I'm going to add them together and get my red vector, get the result. And now I'm going to determine what that force needs to be. And the force that would need to be applied, okay, we would do some, and we would do we'd break down that red vector essentially into its horizontal and vertical components, find out its length using the Pythagorean theorem. We would use right tangent inverse to find the angle that we need to direct our force, and we can get that person from A to C in a much more efficient manner. Okay, does that make sense? It's the same idea. You know, we go back to that airplane question. If my airplane is traveling this direction, it's traveling from A straight to B, but it hits a crosswind of BC, and I don't do anything to correct my movements, the plane is going to end up at C. Okay, so we have to maybe compensate for that in that situation. All right, so a lot of times using the notation of like A vector AB, BC, and that kind of stuff, it gets cumbersome. So that's where we start talking about U's and V's and replacing the names with that notation. But if I ever want to add two vectors together, what you have to do is take your two vectors and you put them tip to tail. Okay? So I've got three vectors here. And let's just kind of maybe just deal with two of them. Okay, so I got vectors U and V here. Okay? And this is on my website. You can mess around with it. You can change these vectors by just grabbing those kind of blue points at the end of the vectors. Make them whatever you want them to be. Okay, so let's say those are my two vectors, U and V. The gold one here might be kind of hard to see, but that is V. If I want to add those two vectors together, okay, the idea here is if you were to put somebody right there, okay, at the origin, and you apply two forces on them simultaneously, okay? So let's say that, like I stand right here, and I'm going to apply the force in the direction of this purple vector to this person in the chair, and let's say that Jackson stands right here, and he's going to apply in this direction a force to that person. So we're both kind of pushing this person in those respective directions. Does that make sense? Can you visualize the course that that person is going to take? Okay, it's going to be a combined effort, and that person, should they not travel kind of down that line? Does that make sense? Okay, and if you were to do this, in actuality, you go out in the gymnasium and do this or something like that, this would happen. Think about, maybe you could do it this way. Let's say we put a rope on this person. Okay, two ropes on them. And one person stands here, another person stands here, and we pull with unequal forces this direction. So I pull in that vector's direction, and the other person pulls in that vector's direction. Isn't this person going to be slingshotted that way? Does that make sense? Okay. So to find out where they would end up, what we do is we take this vector here. Okay, and because right now they're tail to tail. And when I say tail to tail or tip to tail, the tips are the terminal points. Okay, the tails are the initial points. So the terminal points are the points with the arrows on them. Right now they're tail to tail. I want them to be tip to tail. So what we do is we take this vector here, because we know And no matter where I put this vector, it's still the same vector, right? So it's still the same force, it's still the same direction, all that kind of stuff, okay? So if I put that right there, so it's tip to tail, I get that red resultant of u plus v, or v plus u, however you want to write it. And what that means is that if Jackson and I would have done that set of forces to this person in the chair simultaneously, that person, that situation is exactly the same as if I applied this vector to that person first. And once they came to rest, Jackson then applied his force to them, and they came to rest here. Does that make sense to everybody? Okay, so you can do it simultaneously or do it individually. And if I stagger them individually like this, I can visually see geometrically what that result would look like and see where that person would finally come to rest. Okay? Now the idea is it should not matter who applies what force first. Okay, so I'm just going to cut out u plus v real quick. Okay, go back to this. Okay, and let's say that Jackson applied his vector first. That person came to a rest here. Then I applied my force. Is that u plus v the exact same thing as the previous u plus v? Yeah, okay. So what's going on here, guys, is actually the fact that this vector here can be moved anywhere. This vector can be moved anywhere. And what happens is that we get what we call the parallelogram law. Okay, you ever heard that in physics? Okay. Parallelogram law basically says if your vectors are tail to tail, okay, then your resultant is going to be the diagonal of that parallelogram. Okay. Now it's the diagonal of that parallelogram that incorporates your vectors being tip to tail. Because if I look at the other diagonal, let me just put one in here. That would be if I look at that one, that dark purple one, do you see how that's going from either tail to tail of U1 and V, or it's going tip to tip of V1? So I know it's kind of confusing with the notation there. So it's either, if I hide these, you see how that one's going tail to tail of those two vectors? Okay. Do you see how it's going tip to tip of those two vectors? Okay. So the diagonal that we want to be looking at is the diagonal that is going from, or using the sides of the parallelogram that are tip to tail. Those are tip to tail. Or, like we had shown, you can use that portion. Those are tip to tail. So a lot of times they refer to it as the parallelogram law, and then they say, well, do you use what we call a triangle law? Well, the triangle law is just that half parallelogram, right? I never really use the parallelogram, but what I do want you to understand is that when I want to go tip to tail with these vectors, I want to move them around. You can do that in any particular order that you want to. Okay. So let's get back to my initial picture here. I think I had 3 vectors in here. Okay. If I want to go V plus W would look like that vector, right? Okay. Now, is that V plus W, is that the same vector as if I put V there and start V there, put W there? Does that V plus W, does that look like the same one that we had when we started down here? Are those the same thing? So hopefully that proves to you it does not matter where you start doing the addition. Okay. I like to do it at the origin, but you can do it and you can move them anywhere you want to. Okay. So if I can do that, if I can do v plus w, shouldn't I be able to do v plus w and then add to that? Does that make sense? Okay. Now, I don't think the way I've got this set up is really doing it the way I want to, so let me go to another. The way I got that one set up is just showing you the kind of initial singular addition of just two vectors. So let's go with, let's say I've got that vector there. I want to add to it maybe that vector and then eventually add to it that vector. So let me color those. All right, so I just want to go v plus u plus w. V plus u plus w. Okay? So I'm going to start with v. I'm then going to add to it. I knew that was going to happen. Just the way GeoGebra is, because I initially selected here at 0, 0, it won't let my vector move away from there. So let me just kind of adjust this a little bit. All right, so now I can move them back to here. It's kind of dumb, but whatever. All right, so I'm going to v plus u plus w. So start with v. Okay. Now I want to add u to it. Okay, so I'm going to, let me change u. Doesn't make a whole lot of sense, at least right now, to have u going in the opposite direction of v. We haven't talked about that yet. So let's make u that one. Okay, so if I go v plus u plus w, okay, so there's u. So now I go tip to tail. So that would be v plus u, right? So you can see that if I went from here to there, that would be the resultant of those two things, right? Now I want to add w to that. So it just means w gets tacked on to the end. It's not tacked on to the last terminal point. And now you get v plus u plus w. So if I put a person in a rolly chair, apply a vector v to them, they stop here. Then apply a vector u to them, they stop there. Then apply a vector w to them, they stop there, right? Would it be more efficient to start here and apply that vector to them to get to that terminal point? So that would be the resultant. Does that make sense? You can add as many of these things together as you want to, and you can do that in any order you want to. So if let me see here, let me cut and paste that one. Okay, so that one saved that distance. So let me move these around. Let's go w plus v plus u. Okay. Now if I ask it to look for that vector there, is that vector there, even though the order that we did the movements was different, is it the same thing? Okay. If we had a vector that looks like that, it goes in that direction, 4 units. And then I've got a vector in that direction, 4 units. Okay? So I got that blue vector and I've got that red vector. Because they're the same length, maybe I call this vector u, and I call this vector u because they're the same length, but their directions are different, right? I call that one negative u. Okay? And the reason I can call that negative u, let's say that I put a person at that middle point. Okay? I put that person where my cursor is right now. Okay? And I stand on the left-hand side, and I'm going to push it along the vector u. Okay? The blue vector. Jackson stands on the right-hand side, and he pushes it towards the red vector. But we use the same forces. What happens to that person? Nothing. They stay in the middle, right? So those two forces negate each other. So that tells us we can get 0. We can take a vector minus a vector. Does that make sense? Okay. Opposite of vectors, if I have a vector u, and I just change its direction by keeping its magnitude, we rewrite it as negative u, okay, or the opposite of that vector. So that allows us to do subtraction, okay? Because we'll use vector addition with the opposite of u. Adding the opposite is subtraction, right? Okay. So we'll talk about how that can kind of work on Monday. Hopefully, like I said, give you a good kind of concept of what vectors are. We'll keep working with the geometric principles on Monday, and then hopefully towards the end of class on Monday, kind of convert over into the algebraic understanding of it, because the algebra allows us to do the work a lot faster. Okay? But I think understanding it visually with geometry is going to be useful to understand what you're really doing, what the math is telling you when you do it by hand with algebra.